Right, we've hit noon, so we're going to go ahead and get started. Welcome, everyone, to the Physics of Surfing by Cape Fear Museum of History and Science. Thank you so much for joining us today. We're very excited to have Dr. McNamara from UNCW present to us today. Dr. Dylan McNamara is the chair and a professor in the Department of Physics and Physical Oceanography at UNCW. He got his PhD in oceanography from the Scripps Institute of Oceanography at UCSD and has a master's in physics from San Diego State University. He's published over 30 articles in a wide range of fields, from oceanography, economics, ecology, all the way to physics. So we're very excited to have him with us today. Thank you so much for joining us. And with that, I'm going to hand it off to him, and he's going to wow us with the physics of surfing.
All right, thank you, Dr. Roten. And I want to make a special note to thank the Cape Fear Museum. You know, what a wonderful cultural resource we have here in Wilmington that I myself probably haven't taken enough advantage of. And I promise to take more advantage of it after this talk. Appreciate the invite. So this is, a really fun talk for me. Dr. Roten told me to make a talk that was about 30 minutes. And so when I sat down earlier this week to make a talk and I took a look at it yesterday, it was probably coming in at like an hour 45. So I had to do some cutting. And that was after I had removed video of me surfing. I was going to go out and have someone videotape me surfing and put that in there too. So I had to do something to cut the talk down. And part of the reason the talk was so long is because this is a marriage of two of my favorite topics. Physics and surfing. Physics, as Dr. Roten said, I've spent a lot of time in the world of physics. I got a master's degree, I got a PhD in sort of physics applied to the ocean. And then I've been a surfer for even longer than I've been studying physics. I've been a surfer since I was a little kid. So I could talk about this topic forever. And I've even taught a class on it that was an entire semester's worth, and that was not even close to enough time. So trying to figure out what to do in 30 minutes was a bit of a challenge. So what I decided to do to kind of focus my talk and help me pick off topics was to appeal to one of the greatest surfers of all time, someone from the Mount Rushmore of surfing, the surfer that you see here on this first image, Mr. Tom Curren. And in particular, I wanted to focus on one wave that he caught and use that to kind of guide the topics that I'll choose to talk about. And so this wave, those on the call or on the Zoom who are avid surfers will know all about this. So this was Tom Curren's first wave at the very famous surf spot called Jeffreys Bay in South Africa. And just to give you a little bit of the backstory. So Tom Curren, very famous. He won world titles in, I think, 1985, 1986, and 1990. And just an absolute icon. Like I said, he's on the Mount Rushmore of surfers for sure. Not only was he competitively one of the greatest surfers of all time, but he's just an absolute icon. While he was on the world tour in the 80s and in the early 90s, there was a stop of the world tour in South Africa at Jeffreys Bay, but Tom Curren chose never to go to that stop because of the apartheid policy. So in protest, he would never go to Jeffreys Bay. Eventually apartheid ended, and it became clear that Tom Curren was going to have an opportunity to surf this wave, Jeffreys Bay, which is one of the most famous waves in the world. And what makes it so special is that that wave and Tom Curren are sort of the perfect marriage. The way that that wave breaks, which we'll talk about, and the way that Tom Curren surfs go together just beautifully. And in the surfing world, there was a lot of anticipation, the idea that Tom Curren was going to get to surf Jeffreys Bay. And so I'm going to play this video that sets the stage and shows you the first wave that Tom Curren ever caught at Jeffreys Bay. And then I'll tell you what things I'm picking off of that to talk about with respect to physics. So let me play this for you here.
Yeah, because he had this affection for J Bay. He knew what a phenomenal point wave it was. He knew that Tom was the master of the right-hand point. We went there for over a month. We stayed down there. So, there was one of those mountains, one of those swells radar. We got there, I think, a couple days before. Tom was flying in, like, on the moment. We all knew that Tom was coming. And so we were like, it's down there, like, get your cameras greased and make sure they're working because the guy's going to arrive and the waves are pumping. Like, the day before was good, but it wasn't as good as like the afternoon he showed up. We rolled on a somebody just surfing to make sure it actually could shoot a surfing wave, like some goofy footer dropped in, just did a bottom turn and kicked out, and it just would roll. And I said, okay, it's rolling. And then it was the next wave was Tom's first wave, the J Bay paddling out. Paddled out, took off on his first wave, and rode it flawlessly on a board he never did. It takes a certain person surfing to flawlessly ride that wave.
And then the tagline is it takes physics to have all that stuff happen too. For the avid surfers in the audience, that clip right there, when I hadn't seen it in a couple of years, it still brings goosebumps. That's about as cool as it gets. So here's what I'm going to pick off that little clip right there to talk about today. So you heard him say at one point, the day before was good, but not as good as the afternoon that he showed up. So I'm going to talk about sort of in surfing, why that happens, why swell lasts certain periods of time, and how good it is could vary over that time. In the video, you noticed they showed a clip and people were paddling, and then all of a sudden there were waves coming in and Tom Curran took off. And the avid surfers in the audience know the concept of set waves, but I think most casual beachgoers do as well. When you go down to the beach and you look at the ocean, it's not like waves are coming every single moment. There's periods of time when there's large waves, and then there's periods of time when the waves are not large, and then they're large again, and then they're not large. We call these sets in surfing. So I'm going to talk about what causes that. You heard that photographer there, Sonny Miller, referred to Jeffreys Bay as a phenomenal point wave. I'm going to dig into what makes that wave so special. And then to finish off, I'm going to analyze two pieces of the surfing that Tom did there. The way he took off on the wave and the physics associated with that takeoff, and then the cutback he did and the bottom turns that he does, and sort of what physics are involved in those actions. So first, just to kind of orient everyone, we got to get some definitions out of the way. So a wave, is a classic phenomenon that has, it's all over the world of physics. A typical definition would be a wave is a traveling disturbance that carries energy through matter and space in parentheses. So a couple things to point out here. It's a disturbance that carries the energy, not matter. So when we're talking about ocean waves, energy is propagating across the ocean, but the ocean itself is not moving in the net forward direction in the deep ocean where the waves are traveling. It's just energy that's propagating across the ocean. And it says through matter. So yeah, ocean waves, the matter that they travel through is the liquid ocean. There are waves that travel through no medium. Those are electromagnetic waves, light waves, microwaves, etc., that travel through the vacuum of space, but we're not going to talk about that. So that's what a wave is. I just want you to take that away. And then two critical pieces of wave characteristics that I'll be touching on. One is wavelength, which I think most people know, and it is the horizontal distance as indicated in that diagram between two of the same points on a wave. So say, for example, from crest to crest, what that horizontal distance is called a wavelength. And then period is the time that elapses between, say, two crest passing. So if you started a stopwatch when one crest passed, how long would it take until the next crest passed you? And for ocean waves, periods are in the range of 5 to 20 seconds. Okay. I had endeavored to talk about the whole life cycle of ocean waves in my hour 45-minute version of the talk, and there's not time to do that, but I do want to just touch on it a little bit real quick. Waves are a traveling disturbance that carries energy. So where does this energy come from? Many people know that it's storms that create waves, but that still doesn't answer where the energy is coming from. Where does the energy for the storm come from? Well, it comes from the sun. So in some sort of mystical but real sense, when you're surfing a wave, you're riding energy that came from the sun, which is kind of cool. And the reason that the sun is doing this is because the sun differentially heats the earth. It heats the equator more than it heats the poles. And because of this, air moves around to compensate for that differential heating. And once you get air moving around in various complicated ways, these sort of vortices will spin up, which we refer to as low pressure systems. And, they'll start spinning up and the wind will blow, and that wind has energy in it. And then it transfers that energy to the water. And an interesting physics topic that I don't have time to talk about is that transformation. Like, how do you blow wind over an ocean and get that energy into the water? It's pretty cool, but suffice to say, it'll cause the water to start going up and down, and waves are formed. And then waves, importantly, travel away from that storm generating zone and then come into shallow water, eventually break, and are ridden by surfers. Okay, so let's begin here with this first thing I want to talk about. The day before was good, but not as good as the afternoon he showed. So when a storm blows, when wind is blowing over the ocean, it creates a total mess. You have, that picture I drew of a perfect sine wave, we call it, perfect up and down wave. That's not what a real ocean looks like when the wind's blowing. What you could think of the real ocean as, though, is a whole bunch of those waves all smeared in there together. So it's got a ton of different wavelengths and a ton of different periods in that very messy ocean condition. And so in the storm zone, that's true, but then the waves begin to move outside of the area where the storm created them. And waves are, in physics, what you refer to as being, ocean waves are dispersive. That means that the speed at which they travel depends on their period. So in deep water, this is the formula. To get the wave speed in miles per hour, it's 1.75 times the wave period. So if you have a 10-second wave, it's traveling about 17.5 miles an hour in the deep ocean. So this is a really important phenomenon that helps the world of surfing tremendously, because I'm going to play a little movie here to show you what impact this has. So here's a little cartoon showing, imagine you have a storm right here. We have 3 locations, location A, B, and C. Let me just start it and I'll stop it. So in this cartoon sense, so the storm created that mess of wavelengths. And what I've drawn in here is just 3 of them. There's a longer wavelength, a medium wavelength, and a really short wavelength wave. And 3 different periods too, right? Long period, medium period, short period. So they're all jumbled together. And so a lot of times in Wrightsville Beach, we end up surfing at A. We surf really close to where the storm generated the waves, and we see kind of a mess. We can't really distinguish long periods and medium periods. We just see sort of short period, messy ocean conditions. But notice what happens as this band of waves starts propagating away from the storm. When you get to C, it's a very different kind of wave environment. Because the long periods travel faster, they get out in front. And the more time they have to travel, the more they separate. So by the time you get to C, the long periods are there, then the medium periods, and then the short periods. And so this has important consequences. Number one, the amount of time that the swell lasted in A was very short. Right? They were all jumbled together and they went by in a relatively short period of time, whereas at C, you had the long ones first, then the medium ones and the short ones. So the period of time that the swell event occurred was a lot longer. We do see that phenomenon in Wrightsville Beach when there's hurricanes, right? If a hurricane is off the Caribbean and it's generating that messy sea, and then it has time to propagate away and really get stretched out. And so not only does the swell last longer, but the kind of swell that you see after that travel is a really clean swell. Rather than that messy sea, you see really nice, clean separations of the different periods. So first of all, we've answered why, at the very least in this Tom Curran scenario, it was multiple days that this swell event occurred. He's talking about waves the afternoon before, and then he came, or the day before, and then he came some afternoon later. And so the swell had lasted some period of time because of this dispersion phenomenon. But I'm going to show you this in action in effectively real time. Here's a picture of the weather conditions right now in the South Atlantic. And I put a big black star where Jeffreys Bay is in South Africa. And I put a black box around a low pressure system. So there's currently a low pressure system sitting in the South Atlantic right there. So that's the place that was the equivalent of our A location in the slide before, where a really messy sea is being created. And so now what I'm going to show you is a wave model, a modern state-of-the-art wave model that is simulating the conditions on the ocean surface. And what I'm showing you here in this image is the periods of the ocean swell in colors. So the red colors are higher periods. You're getting up towards 17, 19-second periods. And then the yellow colors are shorter periods and so on. So when I play this, what you'll notice is that that low pressure that's in this box right here, it will create that storm situation that I just described. And then as you see the swell propagate out of the box, you'll see the color bands start separating. There'll be multiple storms, in fact, that'll do this over the course of this model run. So there's a storm there right now, and there it's created the swell. And look at that. See how the period bands are separating. You're getting the long periods first and then the medium periods. And there's another storm right there that created some really long periods. Just go through that again. So you see it separating really nicely. So there it's hitting Jeffreys Bay, multiple different periods, long period first. And there's another storm right there that hits Jeffreys Bay. So the periods separate. And then the other thing to take away is that usually the bulk of the energy is not in the very longest period. You know, that longest period, it takes time. The wind has to blow and it takes time to kind of send the energy into the longest period. Usually the bulk of the energy is in the period just short of the longest period. So I suspect what Sonny Miller was referring to was a scenario just like this, where a wave got, the storm generated surf down here, the waves propagated away, and the first bits of swell to hit Jeffreys Bay in South Africa were long periods and weren't quite as big as what came later, just in time for Mr. Tom Current. So this dispersion is an important effect. Okay, now let's talk about set waves. So set waves, here's a picture of Jeffreys Bay in South Africa. And you can see the indication of set waves. This is a really nice clean swell. You can see the indication of set waves on the front side of the image. You see the waves are a little bit bigger. As you go towards the background, there's a dip in the wave heights, and then the waves get bigger, and then there's a dip. And if you kind of look out into the horizon, you can see that there's big waves, and then there's some small waves, and then there's some big waves, and then there's some small waves. So why does that occur? So the reason that occurs is because waves, no matter what, even when you get this separation, there's always some combination of different wavelengths and periods in the swell. So here's a cartoon situation where I'm showing 3 different wave trains: a short wavelength or short period, a medium period, and a long period. And when you add those together, which is what actually manifests in the ocean, you get what's referred to as interference pattern. You get constructive and destructive interference. If you look in the dark blue and say focus on this peak right here, notice the addition of these waves, it lined up just right so that the peaks all add together and you get a really pronounced peak right here. Whereas over here, you're effectively getting no waves whatsoever, because when you add up the wave trains underneath, you've added a peak and a peak with a trough that was even bigger, and they added up just to cancel each other out. So you get this effect. So this is called destructive interference, and this is called constructive interference. So you get the waves kind of grouping together. And when you then take into account the fact that the waves are traveling at different speeds, the different wavelength waves are traveling at different speeds, you'll see that the group itself kind of moves along as the waves are propagating from left to right. So this is actually kind of interesting, because if you really look close, what you might realize is that the individual waves in the dark blue curve are traveling at a different velocity than the group is. And this is the case in the ocean for deep water waves. Their group speed, when I told you before it was 1.75 times the wave period, that's the speed of the packet. The waves themselves, the individual waves, travel twice that fast, 3.5 times the wave period. So when I play this movie, watch what that actually means. So the red dot will follow an individual wave, and the green dots are following the packet. So notice the red wave comes up, grows big, and then goes to the end of the packet and then disappears. And right when it disappears, a new one pops up at the end of the packet. So, surfers have this kind of, I've heard people say this, talk about, mystical waves, like that wave that came to me and it's traveled all the way across the ocean, made it just right to me. No, not at all. An individual wave does not last very long. It kind of comes and goes inside of the packet. It's the group that is important, and waves are coming and going inside of that group the whole time. And it's this phenomenon that gives you set waves. Like these packets are the set waves. And this is a very simplified version of it. In the real world, there's irregularities, but it's still grouping. There's still grouping. Sets aren't always perfectly timed from one to the next, but they're pretty close. And the more organized the swell gets, the closer you get to like a really nice, clean, perfect grouping. So this is why there were set waves at that moment that Tom Crum was surfing and at all moments. Okay, now let's talk about phenomenal point wave. So what I said about the wave speed a moment ago applies in deep water. Notice I had put that asterisk up there that said in deep water, that's the wave speed. When waves get to shallow water, the situation changes. And so by deep water, what I mean is, and I don't have a lot of time to talk about this, but when waves are propagating through the ocean, the water motion goes in circles called orbital velocities. You can think of it, if you put a little rubber ducky in the ocean as a wave went by, the little rubber ducky would trace out a circle as the wave goes by. So those circles exist at depth. They get smaller. The reason they exist at depth is because you have a circle going and it kind of drags the one below it. And that one goes in a circle and drags the one below it. And each time you're losing a little bit more energy as you do this dragging. And eventually you can get so deep that the little circles are effectively gone and you would have no idea that there's a wave above you. So those are deep water waves, unaffected by the bottom. They have no idea that the bottom is there. But as they propagate and get into shallower water, they start feeling the bottom. Those orbital velocities start running into the bottom and there's friction. And so that friction causes the formula for wave speed to change. It now becomes a function of the depth of the water. So here is the formula for shallow water wave speed when waves get into shallow water. And this is in miles per hour. So if you take the square root of the physics constant g, the acceleration due to gravity, multiplied by the depth that the waves are in, and then multiply that by 2.25, you get shallow water wave speed. So to give you kind of just a ballpark number, like if waves are in 1 meter depth, say 3 feet, they haven't broken yet, you take that, that'll give you a wave that's running about 6-7 miles per hour. But the fact that waves, their speed depends on the depth is really, really important, as I'm going to show you. And one other thing I'm going to point out is that how deep waves feel is a function of the period. So here's a plot that shows the wave speed on that vertical axis down below and the depth on the horizontal axis. So you can see on the left-hand side, the speed of the waves is dictated by the period. It doesn't matter how deep it is. But then you cross that dashed line and now the speed starts decreasing and it's a function now of what the water depth is. So that point where you go from deep water to shallow water, ballpark is about 0.8 times the period squared. Okay, so I'm not going to give away too many of my surfing secrets, but this is really, really important and something that a lot of surfers don't realize. The larger the period, the deeper the wave feels, the earlier it becomes a shallow water wave. And as we're going to talk about, waves start bending depending on what the shape of the bottom looks like. So the bending that you see depends on what the period of the swell is. So for example, if you take, say like a 6-second period, 6 squared times 0.8 is about 30 meters. So that's about 90 feet. So 6-second waves, they start becoming shallow water waves at 90 feet of depth. If you double the period, 12-second waves, now they're going to start feeling the bottom a factor of 4 times deeper. So what I say, 30, so 90 feet, so 360 feet. They'll start turning into shallow water waves at 360 feet. So they'll start their bending process and all the things I'm about to talk about way before shorter period waves do. So certain surf spots take advantage of that. That's all I'm going to say about that. But this idea that waves depend on the depth is really important for the waves that you see breaking at the shoreline. Because in this sort of cartoon example, here we have deep water on the left-hand side, shallow water on the right-hand side. So when that wave crest, the dark blue wave crest comes in, the deep water waves, because the speed depends on depth, deep water waves go faster. So that gets out in front of the shallow zone. And so the wave starts kinking and bending. More realistically, for some coastlines that we see or maybe are familiar with as surfers, you can have a situation where you have a shallow reef that on the left-hand picture, you have that shallow reef where the crests are coming in. They start hitting the shallow reef and slowing down, and the right-hand side kind of bends around. And so what you get there is a certain kind of wave where the waves are bending around and focusing on that zone. You can have other situations where you have these really long crest lines coming into a curved shoreline like that, and the waves will start bending around and feeling that bathymetry, because in the deep zone in the middle where the bay is, they'll go faster and they get out in front of the shallow zone. So you'll start seeing effectively the wave crest will start tracing out the shape of the shoreline in that case. And this is really important because in the left-hand case, you're taking the wave crest and however much energy is in there, you're focusing it into a smaller space. So what happens? The wave height goes up, and you tend to get waves that break harder, and you have tubes or barrels. In the right-hand side, you're kind of taking those wave crests and stretching them out. So that energy is getting put into a larger stretch. So the wave height's kind of going down, and you tend to have waves that are a little softer. They break a little bit softer than the waves in the left-hand side. And so images of that on the bottom left is pipeline. And you can kind of see that same effect there. There's a channel, there's a deep channel on the right-hand side of that image. And you can see those swell lines coming, and there's a little sense of which they're bending and sort of bowling towards the peak where pipeline is. So they're doing the cartoon version of what's above them. On the right-hand side, that's a classic point break where the waves are kind of wrapping in, and you can see all down at the bottom, notice there, my cursor, I can't get to work for whatever reason, but if you look at the bottom down by the highway, you see that the swell lines have really wrapped in there pretty obviously. Incidentally, that wave on the right is where Tom Curran is from. So that's the wave he grew up surfing. And this is part of the reason that him surfing Jeffreys Bay was a marriage made in heaven, because Jeffreys Bay honestly is kind of a combination of both of those phenomena. It is a point break that has undulations in the bathymetry that also give it that kind of focusing thing. And you notice when Tom Curran rode that wave, there were moments on the wave where it was not breaking very hard. It was what we'd say is a little mushier, and you could do sort of performance surfing on it. And then there were times, particularly at the end, where he was pulling into the tube and it was breaking a little bit harder. So notice the coastline here of Jeffreys Bay is not just a very obvious bend like the one I showed before. It bends and then comes back and then bends again. And you can even see in this image, there's a focusing happening at the top, and then it kind of tapers in the middle. And then there's another part of the rock reef there where it focuses again. So Jeffreys is this really ideal blend of both of those kinds of wave transformations. Barrels, peeling long, and then barreling again. So performance, tubes, everything, which Tom Curran illustrated so eloquently. Okay, so now let's talk about the man himself. This really sublime takeoff. I'll talk first just about taking off on a surfboard in general and the physics involved in that, and then I'll just make some comments about how this one is even more impressive than a common surfer takeoff. So in order to kind of break this apart, got to characterize the forces on a surfboard. They can pretty much be put into 5 different categories. You've got gravity down, the weight of the surfer on the surfboard and the weight of the surfboard itself. So there's a gravitational force, there's a buoyant force pushing up, there's lift that can get created, which I'll talk about. There can be a thrust force, which I'll talk about, and then there's obviously drag as well. So let's talk first about the vertical forces, buoyancy, gravity, and lift. So the buoyant force is a fairly easy thing to get into your head without getting into any complicated physics. So what I want you to think about is a container of water that is sitting still, as you see in this image here. So if you were to imagine that dashed line right there, asking the question, on that clump of water, what are the forces on that clump of water? Well, there's the weight force. You know, however much that clump of water weighs, that's one force, the gravitational force that it feels. But then obviously there's a buoyant force on that clump of water. And because that clump's not moving, those two forces are in balance with each other. So that tells us very nicely how to determine what the buoyant force is. Because if you took an object that had exactly that same shape and put it into the water in exactly that spot and asked the question, what would be the buoyant force on that object? The buoyant force is the same buoyant force on the left. You know, all the water around it doesn't know that it's an object relative to water. It hasn't changed all the stuff around it that's creating the buoyant force. So the buoyant force on that object is the weight of the water that is not there any longer. Because we know if we put that weight of water back in, it would just sit there. So the buoyant force on an object is, all you got to do is figure out what the volume of your object is, figure out how much that water would weigh, and that's the buoyant force that it would feel if it's totally submerged. So let's think about that with regard to a surfboard. So that board that Curran was riding was ballpark about 30 liters in volume. The density of ocean water is ballpark like 1 kilogram per liter. So the buoyant force is the weight. So if you took Tom Curran's surfboard and submerged it completely underwater, the upward force that that surfboard would feel is 30 kilograms. And if you convert that to pounds, which we're more used to, it's 66 pounds. So that is to say, if you take a surfboard, his surfboard, and sink it completely under the water, the force pushing up would be the same force you'd feel if a 66-pound person was standing on you. So if you want that surfboard not to sink, to go under the water and just be sitting just under the water with a person standing on it, they would be 66 pounds. Curran weighs about 150 pounds. So how in the world is he keeping that surfboard above the water? And those of us who surf quite a bit, you know this, right? Like when you sit on your surfboard, it's not that the surfboard sits on top of the water, it goes down until it gets to a place where not only is the surfboard submerged and you got the buoyant force from the surfboard, but part of your body now is submerged and you get the buoyant force on your body too, and you come to an equilibrium, usually about sort of like just below chest deep if you're sitting on sort of like a modern shortboard. But for Curran to paddle into that wave and take off, how in the world does he get extra force to get the board out of the water? And that's what this lift force does. So lift that's created on a surfboard is very much like, you can think of like skipping a stone across a pond. When you paddle into a wave, the front of the surfboard has a curve on it. It's called rocker. In the nose, there's like a kind of a bending up. So Newton's third law says there's no such thing as a force in isolation. There's always two forces, equal and opposite pairs. So as that surfboard's going in and starts pressing on the water's pressing back. And that pressing back of the water is what provides the surfboard lift to get it out of the water. And so usually as surfers, to take advantage of this, especially when the waves are small, you start paddling and you paddle kind of fast. So you start paddling, take some really strong strokes, and that really gets the surfboard enough lift to get you and the board start to become out of the water. And boaters would be familiar with this too. When you're in your boat and you're going really slow and then you crank the throttle, at first the boat's kind of like pushing against the water, and then eventually that lift is enough to get your boat planing up above the water. So surfboard is the same effect. One of the things I'll point out about that takeoff that Tom Curran did is that he barely paddled into that wave. He was savvy enough to take off late, as casual as you could possibly be, and just know that if he hopped to his feet and there was no fumbles, he would hop onto his feet. Let's go back and look at the picture. So right in this first picture, his board's effectively sinking. So he's just going to hop to his feet while the board is still sinking, but he's hopping to his feet in such the perfect position that the board starts to slide down the wave face and the lift force is there to propel him up. And he's doing this not only late, he's doing it as the wave is breaking over his head, and then, he comes out of that commotion looking like he just drank a cup of coffee, as casual as he could possibly be. So a really impressive takeoff, especially given the pressure. This is his first wave at a spot that everyone's been waiting for. And man, he looks like he could be less concerned. And by the way, it was mentioned in that video, that's the first time he's ever ridden that surfboard too. Pretty impressive. Now let's get to the real bread and butter of Tom Curran. So Tom Curran's famous bottom turn and top turn or cutback. So I'm going to play this video real quick, just so I want you to pay attention to this. So here he is, and he's going to, as he's coming down the wave face, he's going to turn straight, and he starts to slow down. And then as he does what we refer to as a bottom turn, it's like he speeds up magically. Just play that again. Watch him come straight down and look as though he's slowing down. And then as he begins to bend around, he speeds up. Oh, sorry, that was the next one. Oh, technical difficulties, 1 second. There we go. I'll just play this bottom turn one more time. Zoom, it's like he's shot out of a rocket. Similarly, when we get to his cutback, he'll go up to the top of the wave, and it's as if he's kind of slowing down. He's got some speed, but as he starts to do his cutback, it's like he speeds up as he goes through the cutback, and he comes out of the cutback almost with more speed than he had to start. Oof. Beautiful. So how in the world could he do that? Well, this has to do with the other two forces, which we haven't talked about, in particular, the thrust force. Drag is kind of obvious, right? Like there's drag from the fins, there's what you call bottom drag, and the bottom of the surfboard's dragging against the ocean. Thrust is something that comes from this particular fin configuration, which is called a thruster fin configuration. So 3 fins, 1 in the back, 2 on the sides. And that's the fin configuration that Tom Curran has there, that he's using to his advantage to generate thrust. And I want to explain quickly how that happens. And in order to do that, I'll first appeal to an airplane wing. Same exact phenomenon. Only it's not called thrust here, it's called lift because it's in the vertical direction. It's just a name change, but it's the same physical manifestation. So when you have an airplane wing like that, notice it's curved on the top and straight on the bottom. So as air comes and hits that airplane wing, the air that goes over the wing goes faster than the air underneath the wing. The reason for this can be a little bit complicated. The reason it kind of starts off is that when that air goes over the wing, vortices form on the backside, and they kind of spin around in such a way to kind of slow. They're spinning around the wing and running into the bottom side and kind of pulling the top side a little bit. You can think of it almost like a traffic jam. You know, you come in cars and there's a traffic jam at the front of the wing, and then they get around the top and they're like, oh man, let's go. And they kind of speed up. So with that air going faster over the top of the wing, if you think about the air molecules, they're going faster, so they're spreading out like this, compared to the bottom where they're going slower and they're a little bit closer together. So there's the pressure, the density of air molecules is higher at the bottom than it is at the top where they're spread out because they're going fast. So the density is higher at the bottom than it is at the top. So the pressure of them bouncing against the bottom of the wing is higher on the bottom than it is on the top. The pressure on the top is lower. So you have high pressure on the bottom of the wing, low pressure on the top. So that causes a net force in the upward direction, which allows the plane to take off. So for surfboard fins, you have the same phenomenon. When you look closely at those side fins, they have the same shape effectively as an airplane wing. So you have, in this case, you have water coming from the bottom towards the fin. And yeah, there's drag because there's friction of the fin running into the water. But you get this phenomenon where the water that goes around the outside curved part of the fin is going faster for the reasons I just said than it is on the bottom. And because of that, the pressure on the left-hand side of that fin is lower than the pressure on the right-hand side. So you have a pressure force that's from right to left in this image. Now, if that fin was placed on the side of a surfboard, right parallel to the side of the surfboard, that wouldn't be that great. You'd have this force pressing right to the side of your surfboard. But when you look close at the fins on a thruster, they're tilted a little bit. They're not straight back up and down like that. They kind of have a tilt. So that thrust force that we just described, there's a component of it that is in the forward direction of the surfboard. Here's an image showing the back center fin and the 2 side fins, and they're kinked just a little bit. And so that thrust force that we just described, by the way, this is an appeal to what's called Bernoulli's principle. That thrust force that we just described, there's a little piece of it that's helping the surfboard go forward. So let's take a look back again at this bottom turn. This is another image of Tom Curran doing a bottom turn. And so the inside fin that's on the side has a thrust that's in the direction of that green arrow. So what Curran is masterful at is taking advantage of that thrust. You know, just because it's there doesn't mean it's going to be useful to you. If you're not putting just the right amount of pressure on the surfboard and doing just the right amount of stuff, you're not going to really take advantage of that thrust. But Curran knows just how to do it so that that's the reason he accelerated. When he went to go into that turn, he started pointing his fin in a direction that gave him an extra force. And so he started accelerating, and then it got even more force and accelerated even more. Same on the top turn. When he's in that motion at the top of the wave, that heel side fin, the thrust force is in the direction of that green arrow. So what Tom Curran does just beautifully is just brings the surfboard right towards that arrow the whole time. And as he's doing it, he's getting extra force and extra force and extra force. And of course, he's reducing drag in his own special magical way and all these other things. But it allows him to accelerate through that turn because he has this thrust force at his advantage. All right. With that, I could go on, like I said, forever and ever, but I'll stop there. And just say thanks. I hope everyone enjoyed that. I hope the surfers online learned at least something. And I want to just make a plug. I don't know how many younger audience members there are, but if you like this stuff, surfing, studying physics, applying physics to the ocean environment, UNCW is the place to be. You might not want to do the things in that order. Maybe depends, I guess. But I'd encourage any young audience members to think about becoming a college student at UNCW. And with that, I'll end it and say thanks, appreciate it, and entertain any questions that the audience has.
Thank you so much. That was fascinating. And I can see how you could have an entire course on it, because I definitely want to know all the things even more. And I'm definitely going to go look up Tom Curran, because that's really cool. All right. Does anybody have any questions? Feel free to put them in the chat if you do. One question that I have is, where is Jeffreys Bay the best place to surf, or are there other beaches that have that similar physics and landscape that makes it cool?
Yeah, it's a good question. I mean, I think the best place to surf is kind of like saying who makes the best wine or something, like kind of,
Right.
you know, different people have different preferences, and there are plenty of days you go to Jeffreys Bay and it's not great. But yeah, Jeffreys Bay is for sure, partly because it is such a good wave, but also the mystique of it. You know, it's been around and known for a long time. A bunch of famous surfers have been there. A lot of famous rides have happened there. So that kind of puts it into that upper pantheon of really famous surf spots. But there are plenty of other good ways around the world. And we are honestly still discovering them. You know, there's places around in the ocean that have waves that not a lot of people get to see. They're kind of shrouded in mystery, and we're discovering new ones all the time. But yeah, the short answer is Jeffrey Bay is right up there. It's a sort of a bucket list wave that all surfers should probably make an attempt to surf if you're an avid surfer.
Awesome. So we do have a question from Martin Smith. He says, when folks debate about longboarding versus shortboarding, are they emphasizing different aspects of the physics?
Yeah, in some ways they are. That's a great question from my colleague, Dr. Smith. You know, so one thing about longboards is like that calculation I did about buoyancy. You know, longboards, their volume is way, way higher than a surfboard. And you can get longboards that have so much volume that I could almost stand on them without sinking the board itself. So one of the things that longboards are useful for is when you're just getting started, it's a lot easier. It's a lot more stable and a lot easier to ride those things. But, you know, so longboards, I mean, I'm a little preferential to shortboards because it's just what I've always done in my life. Like shortboards have a wide range of waves that they can surf. I would say that's not necessarily the case for longboards. You don't see a lot of guys longboarding at Jeffreys Bay necessarily on days like Kern was just surfing. You don't see a ton of guys longboarding at Pipeline. Shortboards can get into really critical parts of the wave. And if you're really good at that, that's a pretty exciting thing. So in a way, they're just a much more refined kind of surfing with a huge array of things that you can do. Not to discount longboarding. You know, longboarding is, from a style perspective, a very classic way to surf. You know, you're not kind of jumping around and moving your body in all these weird ways. If you're longboarding well, it's a very stylish thing and really cool. So yeah, it's kind of like, I don't know, red wine and white wine, to go back to the wine analogy.
Yeah. We have a comment about the silver dragon in China and how those waves are very cool to watch. If you're familiar with that. Another question, how would the waves be described somewhere near here, like Wrightsville Beach?
Yeah, so one of the things with Wrightsville and the East Coast of the United States in general is that, the ideal places around the world where there's waves are places where the storms are offshore and they're kind of moving in the direction of the coastline. So you get the wave generation from the storm and then it propagates towards the coast. Of course, for us, storms are usually moving off the coast. So we'll get, when the storm comes off the coast, we'll get some local wave generation, but then it moves away and it's sending swell in the other direction. So a lot of the surfing that we do is in the storm itself. So we don't get this benefit of beautifully clean, well dispersed, well separated wavelengths. Sometimes we do when hurricanes occur. So that leads to us not having maybe the most organized waves here in Wrightsville Beach, and we also don't have the largest waves here in Wrightsville Beach. That said, we get a lot of small waves that are friendly for beginners. And the beauty of a place like Wrightsville Beach is that when the waves are really small, because of the way that our beach is, without going into too much detail, small waves are rideable. You take out a surfboard on a really small day here and go ride it, and it's fun. I mean, maybe the simplest thing to say is, like, if you're at Jeffreys Bay, when the waves are really tiny, they're breaking right on top of the rocks. You're not going to be out there surfing. Whereas here, it's always kind of a friendly place and easy to get going on tiny waves. And we do have good days here and there when all the conditions come together. It just happens a lot less frequently.
Next question. Do you know the dimensions on the board Tom was riding that day?
This is one of my friends asking this, I'm sure. I think it's 6'6", 18 and a half or 18 and 3/4, and like 2 3/8, maybe something like that.
Someone else has responded 6'6", so perhaps that's.
It was a 6'6", so I got you there. I have a PhD for a reason.
Yeah. So next question. This was so great. I don't surf with a board, but could you use physics to become a better body surfer? I constantly miss the wave.
Well, body surfing is challenging, and I guess the physics that you would use, that lift concept that I was talking about, is kind of what you're trying to generate when you're body surfing, right? Like when you're swimming into a wave, you want to get going fast enough, and you kind of, the ideal thing to do is you sort of stiffen your body up so the water can start bouncing off of you a little bit. And if you do it just right, you'll kind of skim down the wave face and the lift force will be hitting you and lifting you up, and you can ride for a decent ways. So, things people do to kind of emphasize that is, like, they often will swim into the wave and stretch their arm out so that there's like this underside of your body that's getting that lift force and getting you up out of the water. So just think about that. Think about lift and trying to, you want to swim fast at the very beginning just to kind of get yourself some lift, and then let the wave do the rest of the work and keep providing you lift.
Yeah, cool. So we have another question. Are there particular physics involved when someone gets and stays inside a wave tube?
No, that's all that's all magic. There's no science there. No, I wouldn't say there's particular physics involved. I mean, the fact that waves do that is kind of an interesting phenomenon, and it's one of the places of science and mathematics that we don't have a lot of useful tools to understand in real detail that whole entire process and evolution. When a wave pitches over itself like that, mathematically it becomes a nightmare to deal with. And the reason it does, we didn't talk about this much, but the wave speed, remember, was related to the depth. When it gets in really shallow water, now you get a situation where the bottom of the wave doesn't see as much depth as the top of the wave. So the top starts moving faster than the bottom, that square root GD business. And so if you can have that happen really abruptly, the top moves way faster than the bottom and it spills over like that. And that's what creates the tube. Getting in that thing just requires some skill and just practice.
Cool. So our next comment says, now that I'm in my armchair surfer stage, I have the advantage of living at West Gilgo Beach, Long Island, where I think that's Long Island, where generations of surfers have followed, including a couple of UNCW grads, one of whom started a gear outfit called Thrust, but they've been taken by kite surfing, which should be a subject for one of your future lectures. I've seen kite surfers. It looks really fun.
Yeah, it's getting really popular here in Wrightsville Beach. If you go down to the south end of Wrightsville on a windy day, they're everywhere.
Mm-hmm. Next question, should fin size be determined by rider weight or wave height or something entirely different?
So if you're talking about fin size for shortboards, you're pretty avid, competent surfer. I tend to think that the fin size, I mean, it does depend on the surfboard a little bit. So, but if we're talking about a standard regular shortboard, someone who's a pretty competent surfer, the fin size is mostly a function of the wave size. And a good rule of thumb, as weird as it sounds, is big fins on small waves, small fins on big waves. And the reason for that is a little bit complicated, but you can imagine, like, at the very least, if we're talking about thrusters, the big fins provide more thrust, and that kind of helps you, but it also kind of gives the surfer like something to kind of pivot off of in small waves. Of course, you suffer with a little more drag, but if you can take advantage of that extra thrust, the big fins are nice. And then on larger waves, you got plenty of speed as it is, so you don't quite need as big a fin to generate as much thrust. But yeah, that's a really complicated, that's one of those things where I could do a whole hour lecture on fins for surfboards, fins for longboards, fins and thrusters, fins and twin fins, because the shapes start changing. It gets pretty complicated.
All right, so our last question, oh, no, we just had another one pop up. It says, one interesting thing that I'd be interested in hearing a discussion about is how long period swell often closes out at Wrightsville Beach, where the short periods 7 to 9 have better peaks for taking off and actually making sections.
Yep, absolutely. That's a great observation and a very common thing. And so part of the reason for that is longer periods effectively translate to longer crest lines. And here in Wrightsville Beach, we don't have any point breaks, big changes in the shape of the coastline. So when those longer crest lines come, they just all break at once. Whereas that really messy ocean condition that, in a storm and the periods are shorter, that messy ocean, the crest lengths are not nearly as long. They're kind of more TP. So when those things come, it gives you much more opportunity to have open face to ride on. So if you don't have any undulations in your coastline, yeah, you want shorter periods. But if you're in a place like California where there's all kinds of undulations in the coastline, longer periods tend to be better.
All right. Looks like we have one more. It says, following up, how would you model the way the wave bends over itself? Do you think a computational fluid dynamics simulation could handle it? And could you use that to inform surfboard design?
Yeah, good question. So that's kind of a two-parter. So the wave bending over itself. So traditional computational fluid dynamics breaks down when a wave bends over itself because, if you think about math, it sounds like you might know whoever asked this question a bit more. So, the function is double valued when a wave bends over itself. So you can't use a traditional analytic approach to solving that sea surface scenario. But there are computational fluid dynamics approaches where called lattice-Boltzmann models that have like little particles and they're all moving around. I've never seen those. I don't know that those can. It's a good question. If you're going to make progress, it's these sort of more lattice-Boltzmann approaches to modeling waves folding over on themselves. And then the second part of the question was, what was the second part of the question?
Could you use a fluid dynamics simulation to inform surfboard design?
It's so difficult because the water that's moving under a surfboard is pretty complicated, moving in all different directions. There's all kinds of turbulence. I think that still the kind of empirical piece of surfing is way far out in front of the theoretical piece. And it's going to be a while before the theoretical piece catches up. And that is to say, just going out and riding the surfboard, getting a feeling for what it does is giving us more insight than trying to put that shape into a model, run water, simulated water across it in a couple different directions. You might see some real basic things, but all the nuances of like what the fins are doing and the water's going from this direction to this and the surfer's pressure, it's going in the water more, it's coming out of the water, it's tipping onto the rail on both sides. It's really, really complicated. So I think it's going to be a while before people are running computer models and saying, hey, let's redesign the surfboard this way. I think that's still going to come mostly from empirical data.
Awesome. Well, I think that covers all of our questions. We have one comment. Thank you. This was great. which I would echo. This was very informative and not something that I think I've ever thought about in terms of all the, I didn't know Bernoulli was involved in surfing. Probably should have, but didn't think about that. Another comment says outstanding. So again, thank you so much, Dr. McNamara, for joining us today and delivering that. And we hope to see you again with a different, maybe a part 2, where you can touch on all those topics that you didn't get to today. So
Yeah.
thank you everyone for joining us this afternoon. And we will hopefully see you at the museum sometime soon. All right, everyone have a great rest of your day and a great weekend. Thank you.